All right, so this is lesson 1.3 and really a key lesson, so an ideal geometry. So you guys will want to draw this little diagram here on the right-hand side, right? And what we're really doing is setting up what geometry is all about. So it doesn't have to be pretty and beautiful, but you want to write it, and then we'll talk about each individual part. And it's like a building. It's from the bottom up. So the bottom says undefined terms. And there's 3 of them. And you can abbreviate if you want. And we already did the undefined terms. If you remember, they were a point, a line, and a plane, right? Were the 3 undefined terms. Next, you get definitions, and there's a whole lot, and we've had a bunch of them already, right? Like parallel lines and stuff like that. So definitions, you can go just DEF, and then postulates, that's the next level. And it says about 2 dozen, you can put about 24 if you want. And then the top part are the theorems, of which there are many. Give you time to get there. Okay, so this is how the geometry is built. And the idea of geometry is that if we'll use only things that we know to be true, then our conclusions will have to be true. And so you start off with undefined terms, those 3 things that you got to start somewhere with. And then we add definitions, things that are obviously true. Then we get to postulates, and I'm going to explain them in a minute. And then finally, we get theorems. A theorem is like a hypothesis. You know, if such and such takes place, I think this will result. And what we do in geometry is we use the definitions and the postulates to prove that the theorems indeed are true. And therefore then we keep showing everything to be true, and we therefore then are able to build a structure that we know is true. So that's the key. So let me break it down a little bit, and then I'll explain it one more time once we look at the whole big picture. So A is going to be postulates. Postulates. And then make a parentheses and write axioms, A-X-I-O-M-S. So when we talk about a postulate, somebody might say axiom, we mean the same thing. Axiom, postulate, they're interchangeable. All right, so you can use either one. What are postulates or axioms? They are, and I'm going to use green here, they are basic, back to blue for a few words, basic relationships that are and then grab your green again, and this is the key, assumed to be true. Assumed to be true. And assumed is the key word there. So here's the thing. Our definitions we assume to be true. Our postulates we assume to be true. So they're assumed to be true. So if there's any weak link in our geometry, because remember, we want to end up with truth. Right? Where we want to end up, we want to make sure that our conclusions are true. Well, we got to use some postulates to end up with proving something to be true. And so if perchance a postulate is not true, then we're not going to end up with truth. But again, we're going to assume they all are. And look, geometry's been around for a long, long time, and people have worked on these things for a long, long time. But again, if there is any weak link, it is in a postulate. Transpose that over to real life, and is there a danger in real life when a person assumes something to be true, but it's not? Yeah. And our world's full of people today that make some basic assumptions. Like a lot of people assume God doesn't exist. And they assume that that's true, and it's not. And now a lot of other decisions they make on their life are based upon that false assumption. And therefore, they think they're doing the right thing or thinking they're coming up with a true conclusion, and they're not, because their postulate to begin with wasn't. So postulates are basic relationships that are assumed to be true. And throughout the course, we'll get a bunch of these postulates. But the key is we're going to use them to help prove the theorems, and that's the key to geometry. All right, before I get to that theorem part, a couple things here with the postulates, because they should have 3 characteristics. So number 1, they should have 3 characteristics. And I'm going to write these in green. They should first off be consistent. And then comma. Second, independent. And then third, complete. There's nothing earth-shattering there. You don't want a postulate that's true sometimes and not true other times. Right? If I say that you're consistent in something, like, let's suppose I said that student A is very consistent in turning in their homework. What am I saying? I'm saying that almost all the time they turn their homework in, right? They're consistent in it. So we want postulates that are consistent. We can't have a postulate out of something that's true 80% of the time and not true 20%. It wouldn't be consistent, and we can't use it. It's got to be consistent. Independent means we don't want extra postulates. We don't want 3 postulates that all basically say the same thing. We don't need it. Now we're making it too big and too complicated. And so we don't want that. So we want independent, and then we want it complete. So let me define complete here. And what we mean by complete is it forms a sufficient base for a full description. Forms a sufficient base for a full description. For a full description. Okay, and I'm going to write a statement here in red because you're going to see this again. All right. Every useful postulate I'm going to go to blue, is consistent comma. Go back to red for one word. Some, and then back to blue, are independent. So every useful one's consistent. Some are independent. And then lastly, comma, and then finish in all red. But none are complete. And the author of the course expects you to know that. All right, so, and that's why I put it in red and I put an asterisk by it. They want you to know that. All right, so though postulates are supposed to be consistent, independent, and complete, it's impossible to have every postulate be all three. And in fact, none of them are quote unquote complete. All right, just accept it. We don't need to really go into any more than that. It's just that's the concept and that's the idea. Let me add a few words here to help you with things. When we say consistent, they don't contradict one another. Don't contradict one another. So consistent, they don't contradict one another. And then independent we'll talk about here in a moment as well. But independent, basically the key here is you can't get one from another that you already have. In other words, and that's what I was trying to say, independent. Say we have a postulate 7. If it basically says the same thing postulate 9 says, we don't need 9. They say the same thing. Independent. So when we say independent, it's basically the long definition is no postulate can be deduced or proved from the other postulates in the system. They have to stand alone. So you can't get them from the other. All right, we'll practice all that in a little bit, and we'll go into that a little bit more here in just a moment. So that's postulates. Then capital B, theorems. These are statements shown to be true and then we'll finish in red by a proof. So a theorem is something you think is true. You know, if you take it biblically. So here you understand something, you think something is the case. And what do? You get your Bible out and you search it out and you see if indeed it is the case. And you're taking your Bible and you're trying to prove whether or not what you think is true by what the Bible says. That's kind of the idea. A theorem is something we think is true and we're going to prove from things that we know to be true, postulates and definitions, to see if indeed it does turn out to be true. A more practical way would be doing an experiment. You think if you mix these chemicals, you'll get something out. Okay, mix the chemicals and see if indeed you get something out. Prove if indeed it is the case. So that's what theorems are, things that have to be proved. And so that's how the geometry is built. And all of this, remember, is designed to help us to think more logically and clearly. All right, that's the whole idea there and the whole thrust of it all. All right, so with this, let's see if it's here. Should have some examples, if I can find them. Ha! Way down there. All right. No problem. All right. And that's what, example 2. So where in the world was example 1? Let me back up here. I'm interfering with my recording here, so come on. Come on, board. You can do it. All right, let's see. Man, where is my example 1? Can't find it. All right, let's go another route. Oh, there it is. All right. Okay, so let me just deal with it here where it is, and we'll make it work. All right, so example 1. Determine whether the following set of postulates is consistent. So notice we're after the idea of consistent. So once again, it doesn't contradict one another. So they gave us 2. Because to be consistent, this one can't contradict this one. Right? And so when you're asked, is a postulate consistent, you have to think back of all the other postulates and see if there's any contradiction. Here they gave you 2 to compare. All right, so we got to look and see, do these contradict each other? So postulate 1, if 2 lines intersect, then every other line in the plane intersects one of them. Okay, so when you do stuff like this, it helps if you can draw a mental picture or draw an actual picture. So, we got a plane. And it says if 2 lines intersect, then every other possible line in the plane intersects one of them. That's the first one. The second one says if 2 lines intersect, then there is exactly one line parallel to both. So again, you got the same scenario to begin with. If 2 lines intersect, then there is exactly one line parallel to both. All right, let's see what the answer is. According to postulate 1, every line in the plane must intersect one of the 2 intersecting lines. Yes, that's what it says, right? However, postulate 2 requires a line that is parallel to both. And therefore, if it's parallel to both, is it intersecting either one? Right? Would you agree, right? Parallel means they don't intersect. Yes? So again, we're not trying to see whether it's true or not. We're just trying to see if it's consistent. And so postulate 2 requires that a line parallel to both doesn't intersect either, since these postulates lead to contradictory conclusions, right? The first one says, hey, every other line has to intersect both. And the second one says, no, there exists a line that's parallel to both. Well, that's a contradiction. All right, so therefore then, not consistent. That's not easy, I understand, right? Jathan's probably going, oh man, that's way out there. Yeah, I understand. This beginning stuff is more difficult than the geometry becomes as time goes on. So hang in there and just try to get a grasp of the major idea, and you will find it will get easier as we go down the road with the concepts. Okay, here's the second example. So now we're checking for independence. So remember, independent means one postulate can't be derived from the other. So let's look at postulate 1. If an animal is named Polly, then it's a parakeet. Okay, whatever. If an animal is a parakeet, it's a bird. Okay. If an animal is named Polly, then it's a bird. So the question is, are all 3 of them independent? Are all 3 independent? And I'll look at the answer in a minute. I'm not sure exactly what it's going to say, but we'll look. If an animal is named Polly, then it's a parakeet. And if a parakeet is a bird, then from these two, we already know the third one. Right? So there's no need for the third one. Because the first one said, if you got Polly, it's a parakeet. And the second one said, every parakeet's a bird. So therefore, we don't need a postulate that says Polly is a bird. Because 1 and 2 together tell us Polly is a bird. All right, let's see what their answer is. Come on. My systems are fighting each other. Come on! All right, the third postulate is logical conclusion that can be derived from the previous. So the postulates are independent. Yeah, just what I thought. We don't really need the third one. So again, with a postulate, you want as few as possible. You don't want extra. All right, again, that can be tricky. Now, one more thing with our course, and this isn't uncommon for high school courses. There are some things that should be a theorem. And remember, every theorem needs to be proved. But the proof is so difficult that in some high school courses, they instead call the theorem a postulate. Because technically, we're supposed to prove every single theorem. And because they're so difficult to prove, though you can be proved, some high school courses will call some theorems postulates. You get to college, it might be a theorem and you're stuck proving it. All right? And no big deal, just a kind of a statement that you understand that such is the case. Come on, board. All right. We can't be ready for an exercise already. Nope. So everything is kind of cattywampus here. All right. So let me go back if I can. Now I need a blank page. Okay. So was all that underneath letter A, because I changed my notes, was everything we've done letter A? Huh? A and B?
Yes, sir.
All right, so next is C. Okay, so letter C. So now let's get into some postulates. So C is the incidence postulates. INCIDENCE postulates. All right, first one. Every postulate has a number, and some of them have a name. And the numbers to the postulates depend upon the course maker. Whoever makes the course numbers them according to when they come in the course. So I remember I used to have geometry students where that they would learn the postulate numbers because it would actually makes it easier to remember them, and it also makes it easier when you're given the reasons in a proof. You could just put the number down. But some of them thought, hey, if no matter what geometry course I'm looking at, postulate 3.2 is going to be the this same postulate. No, it's every author numbers them according to their course. So, for example, our course, this is P for postulate 1.3.1. Great. And the name in parentheses is the expansion postulate. And I'm just going to go P for postulate. And there's 3 parts to it, so let's try to use 3 separate lines. All right, first line, A, and I'm going to go to red for the word line, a line. And if you use your color here, I'm going to try to stay with the colors to help you associate some things, and then go back to blue after you do the word line. Contains at least, and you should know this one already, contains at least, then leave a little space, and then write points. So how many points at least does every line contain? Two. All right, so every line contains at least 2 points. That's the first postulate. And that's, again, knowledge that pretty much everybody knows. We don't need to prove it's true. It's an obvious truth. The second part is and then I'm going to go to green for the word plane. And if you squeeze plane in enough, we can use dittos for contains at least. And then we can't just go points here. But how many points does it take to determine a plane? 3. So now we're up to 3. But now we got to add a little bit more, so keep your green. 3 non-collinear. And then finish off in blue, points. So a plane contains at least 3 non-collinear points. And then finally, black, space. And then dittos contains at least. And what do you think space is going to be? How many points? No, at least, right? Because a line has infinite number of points, but a line is at least 2, a plane is at least 3, and space is at least 4. And what are we going to say? What kind of points?
Non-coplanar points.
Non-coplanar points. Because if all 4 are in the same plane, we don't know where space is. Space has to be 3D. So 4 non-coplanar. And hopefully that makes sense. And that is the incidence postulate. So if you got a little bit of room here off to the side, give yourself a little plane. Let's call it plane, I don't know, Q. Remember, we can name a plane with a lowercase letter. Take your red and make a point A. And make a point B, and then take your blue and draw a line through them. Right? Because we know that every line has at least 2 points. So if we've got a line in a plane, we know we got at least 2 points in the plane. Take your red and take another point outside or off of the line and in the plane and make it C. Do you see now how we know where plane ABC is? Right? Because we have 3 non-collinear points. And then if we take a last point, I don't know, D, and stick it up here, you see now how we have space? Because D's not in the same plane. And that's how you get non-coplanar. 3 in the plane, 1 outside. Now we know where space is, right? Everything, not only just all the points in the plane, but all the points around the plane as well. All right, no big deal. This first expansion postulate may come up in some proofs, but it's pretty basic. So a line, 2 points, a plane, 3 non-collinear points, space, 4 non-coplanar points. All right, second one, P 1.3.2. See, we're in section 1.3. That's where the 1.3 comes from. And then 1 was the first one and 2 is the second. And that's why, again, the numbering is where the author puts it in their text. So, but the name is pretty common, and this one is the line postulate. And this one simply states this: any 2, and then I'm going to go back to red again. Any 2, just leave it blue. Any 2 points lie in exactly and then finish in red, one line. Any 2 points lie in exactly one line. This one's pretty easy to understand. You know, if you got 2 points, I'm going to stick a point A here and a point B. Guess what? There's only one line that goes through those 2 points. No other line goes through those 2 points except that one. There is no other line. Right? I mean, you don't need to draw it, but that one doesn't go through both points, and that one doesn't go through both points, and that one doesn't go through both, and that one. There is no other line that goes through those 2 points except for that line. That's the second postulate. Again, feel free to ask questions if you're wondering as we go. But that's pretty obvious. All right, third one. Again, these we don't have to prove. Postulate 1.3.3. And its name is the plane postulate. Plane postulate. And again, you don't need to keep writing out the word postulate. You can just do capital P. Plane postulate. And this one is 3 non-collinear points. 3 non-collinear points lie in exactly, and I'm going to use my green to finish with what words? What makes sense to your brain? One plane. You know, so on this one, what they're telling you is, if you've got 3 points that are not along the same line, there's only one possibility for the plane that they're in. They can't be in anything else. And I can illustrate this best with some sticky tack. If I can find sticky tack. My sticky tack's not too sticky. Sticky tack gets pretty hard. All right, let's see. See if I can do this. I don't know if it's going to show up on the camera or not. I'll try to do it up here. All right, take a point here. All right, point. Take a point here. Point. Now there's a line that goes through those two, so I got to take a point, not put it on the line there, right? You see how the plane of the board is the only plane that goes through all 3 of them? There is no other plane, no matter what. And again, I like to use a folder to illustrate a flat plane, right? Because it's a flat surface. I mean, this one goes through those 2, but not that one. You know, this one goes through those 2, but not that one. Goes through those 2, but not the third one. You know, through 2, but not the third. The only one that goes through all 3 is the plane of the board. Does that make sense? So that's all they're trying to say. That's all they're after there. All right, so 3 non-collinear points lie in exactly one plane. Fourth one. This is the flat plane postulate. The flat plane postulate. And this one says, if 2 points lie in a plane, so now we're getting to an if-then situation. So I'm going to underline the if in red. And I'm going to take the word then and underline it in red. Geometry is full of a lot of if-then situations. Now they're telling us, hey, we got a condition. If this condition is met, then here's the conclusion. If 2 points lie in a plane, then the red line containing them lies in the And then finishing green, same plane. The line containing them lies in the same plane. So go ahead and draw this. I'm going to do some wording here with this, some symbology. Give yourself a plane. We'll call it plane lowercase p. Stick a point A in there and a point B in there. So let me do some symbols to explain this postulate. If A and B are an element of plane P, right? Well, let's add something here. Take your red. Let's draw a line through A and B. And let's give it a name of lowercase k, right? Because we could name the line a different way. Then line K what symbol is that?
Subset. Oh, that's it, yeah.
Subset. Line K is a subset of plane P. All right, so what we did was we did it all with wording, with symbology. So all it's saying is if 2 points lie in a plane, then guess what? The line containing them has to be in the plane. And if the line's in the plane, the line's a subset of the plane, right? So we equated the line has to be in the plane to the line being a subset of the plane. So we really taught you two different things there, but they relate. They're interconnected. It amazes me how they expect this lesson to be in one day. There's a lot of stuff here. No. Let's see. Come on, board. Board, you are. Oh man, it did do it. All right, let me go back. Yeah, we're not there yet. We are not even close yet. All right, let's go to 5. We got 2 more incidence postulates. Man, oh man. All right, number 5. Postulate 1.3.5. And this is the line intersection postulate. Line intersection postulate. Now this one makes complete sense, and you know this already. If, and then I'm going to go to red, 2 lines. Go back to blue for a few words. Intersect. So the name goes along with what's happening, right? If 2 lines intersect. Then their intersection is exactly and the way it finishes is 1 point. showing up. So you got one line, right? If these two intersect, there's that one point, right, where they intersect right there at that point. So here's what we're not saying is possible. Do you remember at Algebra 2 how you could be consistent and dependent? Two lines that are the same line. In geometry, the same line is the same line, and therefore you only have one line, you don't have two. So in algebra, though, we can have two equations that are produce two lines that are exactly the same line. In geometry, we only consider that as one line, so that we don't have an infinite number of intersections like you would in algebra, because those two lines are the same line. Any line that goes through the same 2 points is the same line in geometry. So the only other possibility then is if they intersect, they got to intersect at a single point. That's the only possibility. There is nothing else. All right, and I'll have to pick up here tomorrow.